Hello again. In our last lecture, we did a little thought experiment, and we tried to quantify the amount of information that came in the form basically of a yes or no answer to a question, right? And we said that really that's one bit of information. Why? Because that's the amount of information that the sender would have to convey to the receiver to completely remove the receiver's uncertainty about whether the answer was yes or no. So we're going to continue this thought experiment a little bit now. Okay, so let's look at some more complicated messages. For example, suppose that we wanted to send an n-bit binary number. How much information is contained in that? Well, it's pretty clear, if you could have arbitrary n-bit binary numbers, that you're going to need to send n bits of information. That just makes sense, right? That's pretty obvious. But let's make it a little more complicated. Suppose we're trying to send a single decimal digit. Well, how many bits of information is that? Well, let's see. We have 10 different possibilities, 0 to 9. If we tried to represent those as a binary number, for example, 1 bit wouldn't do because there's only 2 possibilities. 2 bits wouldn't do, there's only 4 possibilities. 3 wouldn't do, there's only 8 possibilities, and we've got 10 possibilities. 4 is enough, okay? And so we could easily represent the information in a single decimal digit with 4 bits of information, right? But actually that's overkill because there are 16 possibilities there. So is the amount of information in a single decimal digit 4 bits of information, or is it 3-point-something bits of information? Well, we'll come back to that question later. Well, how about a 2-digit decimal number? Well, we've got, the first digit and the second. If we can represent each of them in 4 bits, then we ought to be able to easily represent a 2-digit decimal number in 8 bits, right? But we don't have to, because with 2 digits, there's 100 possibilities. We could do that in 7 bits. So there's some subtlety going on here. And how about the last one here? The attack is at dawn. Well, gee. I mean, we could surely send this in ASCII. There's 21 characters there, and so that's 8 times 21, whatever that is, right? But presumably there's less information than that in this message. Well, how much information? Well, that's pretty hard to figure out. Well, let's try to take a slightly different take on this. Suppose that we have our sender and our receiver with a channel between them, and the sender and the receiver have agreed that the sender is going to send one of exactly 16 possibilities. Well, okay, that's easy enough, right? We got 16 possibilities, 4 bits ought to do it. In fact, we can code each of those 16 messages explicitly as a 4-bit string, and that ought to work just fine. So we send those 4 bits of information. Well, what's happening? Each time one of the bits gets sent, right? Consider that the first bit, the bit on the left, gets sent. What's happened? Well, the receiver has 16 possible messages that might be coming in. As soon as that first bit is received, the message space gets split in half, right? So if you got a 0 as the first bit, then you know it's one of the 8 messages on the left. If it's a 1, it's one of the 8 on the right. Okay, well, say it's the ones on the left. Then the next bit tells you which 4, either the top half of that column or the bottom half of that column. And so what's happening is each time you receive a bit, you're splitting the search space in half. And you can only do that so many times. In this case, you can only do that 4 times until you get down to exactly 1 message. Right, so that's a key observation. Because if you think of what's happening here as a search problem, we have a certain list that we're going to search. Each time we're dividing the list in half, either the first half or the second half, you can think of that as being represented in a binary tree like this. And so each time you send one of the bits, you either go to the left or you go to the right, and that divides the search space in half, assuming that the tree is balanced, that is a complete binary tree. And the longest path in a binary tree like this is the ceiling of the log base 2 of the number of leaves of the tree, right? And so what that tells us is that in some sense, the amount of information that you're sending in a message has something to do with the log base 2 of the size of the number of possible messages. Okay, so if you knew that the sender and the receiver had agreed in advance on all the messages that could possibly be sent, and they both knew an encoding, i.e. just number them, as binary numbers, then the content of a message which told the receiver which of those messages it was would be something like the ceiling log base 2 of k, where k is the size of the message space. But they must have agreed, notice that they must have agreed on the encoding in advance. Okay, so then we come back to that message we looked at the beginning, the attack is at dawn. How much information is in that? Well, now we can see that the answer to that question really depends upon the amount of uncertainty in the receiver. So if, for example, there were only two possibilities, either the attack was going to be at dawn or at dusk, then you only really need to send one bit of information to tell the receiver which it is. On the other hand, if there's much more uncertainty, like the attack could come at any time, then you're going to send lots more bits of information, because one isn't enough to completely remove the ambiguity in the transmission, right? This is a great quote from Warren Weaver, one of the founders of this information theory area. He said, "The word information relates not so much to what you do say as to what you could say, i.e. to the size of the message space. That is, information is the measure of your freedom of choice when you select a message." And I think if you get that point about information theory, a lot of the other aspects of this theory become more straightforward. Okay, so what have we said? Well, the information content of a message really is about the amount of information it contains, or the amount of uncertainty that it resolves in the receiver. And in an ideal situation, if you knew in advance exactly what messages could be sent, you could be very efficient, and each bit would reduce the search space by half. That's pretty good. Unfortunately, in most communication situations, you don't have that scenario. For example, in the example we just looked at, we don't know how many possible messages could be sent. And so we may have to have a much less efficient encoding, like ASCII, for example. Thank you.